Every time you unlock your phone with your face, every time Google translates a sentence, every time ChatGPT writes a paragraph, a neural network made a prediction. But here's what most people never ask. How did it learn to do that? How does a pile of numbers go from random noise to recognizing a cat? The answer is one algorithm. It's called backpropagation. Let's start simple. A neural network is a stack of layers. You have an input layer. This is your data. Pixel values from an image, words from a sentence, numbers. Then you have hidden layers. This is where the magic happens. Each node takes inputs, multiplies them by weights, adds a bias, and passes the result through an activation function. Think of weights like volume knobs. Each one controls how much a particular input matters. A big weight means, pay attention to this. A small weight means, mostly ignore it. Finally, there's the output layer. This is the network's answer. I think this is a cat. I think the next word is the. I think this email is spam. But when you first create a network, all the weights are random. The output is garbage. The network doesn't know anything yet. So how does it learn? Learning starts with a forward pass. You feed data into the input layer, and it flows forward, layer by layer, until you get an output. Let's trace one. Say we have a tiny network, 2 inputs, 1 hidden layer with 2 neurons, and 1 output. We'll use actual numbers so you can follow along. Input 1 is 0.5. Input 2 is 0.8. Each connection has a weight. Let's say the weights to the first hidden neuron are 0.4 and 0.6. So the weighted sum is 0.5 times 0.4 plus 0.8 times 0.6 equals 0.68. We add a bias, let's say 0.1, giving us 0.78. Then we push this through an activation function. We'll use sigmoid, which squashes any number into a value between 0 and 1. Sigmoid of 0.78 gives us roughly 0.69. We do the same for every neuron, layer by layer, until we reach the output. Let's say our network outputs 0.82, but the correct answer was 1.0. The network was wrong. And now we need to measure how wrong. To measure the error, we use a loss function. The simplest one is mean squared error. You take the difference between what the network predicted and the actual answer, and square it. Our prediction was 0.82. The target was 1.0. The difference is 0.18. Squared, 0.0324. That number, 0.0324, is the loss. It tells us how badly the network performed on this one example. The entire goal of training is to make this number as small as possible. And to do that, we need to figure out which weights cause the most error and adjust them. This is where backpropagation begins. Here's the core idea. We want to know, if I nudge a specific weight up or down just a tiny bit, how much does the loss change? It's called a partial derivative, and the technique for computing it is the chain rule from calculus. Don't worry, you don't need to be a calculus expert. The intuition is simple. The loss depends on the output. The output depends on the weights in the last layer. Those weights depend on the activations from the layer before. And those activations depend on the weights in that layer. It's a chain. So to find out how a weight deep in the network affects the loss, we just multiply the effects along the chain. Loss to output to weighted sum to weight. That chain of multiplications, that's backpropagation. We start at the loss, and we propagate the error signal backwards through the network, layer by layer. Let's actually do it. We'll work backwards from the loss. Step 1. How does the loss change with respect to the output? The loss is the squared difference. Prediction minus target, squared. The derivative is simply 2 times prediction minus target. That's 2 times 0.82 minus 1.0 minus negative 0.36. The negative sign means increasing the output would decrease the loss. Good. We want the output to be higher. Step 2. How does the output change with respect to the weighted sum before the activation? This is the derivative of the sigmoid function. For sigmoid, it's output times 1 minus output. That's 0.82 times 0.18 minus 0.1476. Step 3. How does the weighted sum change with respect to a specific weight? That's just the input that weight is connected to, the activation from the previous layer. Let's say that was 0.69. Now we multiply the chain. Negative 0.36 times 0.1476 times 0.69 minus 0.0367. That number is the gradient for this weight. It tells us this weight should increase because increasing it will reduce the loss. The magnitude tells us by how much. Now that we have the gradient, we update the weight. The rule is simple. New weight equals old weight minus learning rate times gradient. The learning rate is a small number. Let's say our learning rate is 0.1. The old weight was 0.5. The gradient was negative 0.0367. New weight equals 0.5 minus 0.1 times negative 0.0367 equals 0.5 plus 0.00367 equals 0.50367. The weight went up, just a tiny bit, and that tiny nudge makes the network's output slightly closer to the correct answer. Now imagine doing this for every single weight in the network. Hundreds, thousands, millions. Every weight gets its own gradient. Every weight gets nudged. That's one step of training. And then you do it again, and again, thousands of times. Each time, the loss gets a little smaller. The predictions get a little better. The network learns. So the full training loop looks like this. 1. Forward pass. Feed data in, get a prediction. 2. Compute the loss. How wrong were we? 3. Backward pass. Backpropagate the error. Compute gradients for every weight. 4. Update weights. Use gradient descent to nudge each weight. 5. Repeat. Next batch of data. Thousands of iterations. This loop, forward, loss, backward, update, is the heartbeat of every neural network ever trained. GPT, DALL-E, AlphaFold, self-driving cars, all of them learn this way. The architecture changes, the data changes, the scale changes, but the core algorithm? Backpropagation and gradient descent, every single time. Here's one more way to think about it. Imagine you're standing on a hilly landscape in thick fog. You can't see the bottom of the valley. You can only feel the slope under your feet. Gradient descent says, take a step downhill, feel the slope again. Take another step. Keep going until you reach the lowest point, the minimum loss. Each weight in the network is one dimension of that landscape. A network with 1,000,000 weights means a 1,000,000-dimensional landscape. You can't picture it, but the math works exactly the same. And backpropagation? That's how you feel the slope. It computes the direction of steepest descent, so gradient descent knows which way to step. That's backpropagation, the algorithm that teaches machines to learn. Next video, we'll go deeper, inside a transformer, and see how the attention mechanism actually works. That's the architecture behind GPT, Claude, and every modern language model. If this helped, subscribe so you don't miss it. And drop a comment. What algorithm should we visualize next?